properties again. And it's not gonna do. Okay, there we go. Oh my gosh. You know, if there's one thing I hate in this world, it's my microphone's not working. But I think I got that resolved. But this I did not write any part of this, but whoever did this, thank you, because I do understand a bit more now. Mainly this part, this dimensional v, as the dimension of the. Okay, so now I understand that the dimension of the vector subspace is the dimension of the image space plus the dimension of the kernel, which is good and useful because we'll need this later. In fact, I'm going to leave this part up on the board here. Don't mind if I erase this part, however, because we're going to be looking at precisely that. We're going to be looking at kernels, dimensions, vector subspaces, that sort of thing, because I am really, 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 really bad at it. Actually, you know what? I think I think that erasing this would be that's more correct. Okay. So we need to define what a vector subspace is. So we have three conditions. If it's a vector subspace, number 1, number 2, and number 3. There's like a whole like Reddit or 4chan forum about it, like random stuff is a vector subspace. So first condition. This one's the easiest. Actually, no. This was the second easiest for you. There exists a zero vector. So this is our zero vector. So the first condition is that our vector subspace has a zero vector within it. Our second condition is, well, closed under addition. This one, in my opinion, is the hardest one to prove. Not too bad, but it is a bit abstract at times. Definitely something I need to work on, and a lot of other people need to work on. And then number 3, there exists a scalar multiple for which C is within the real subset, or within the real number set. Yeah. The one good thing about linear algebra, which I hope I don't get many ideas for, is that it does not use complex numbers ever. If it did, I would probably end myself. Okay. I need to pull up the example as well as promote the stream. Okay. No one's watching. Okay, that's right. Alright. So, this is about... Oh, I'm sorry, I'm on my phone. I need to promote this live stream. I don't even know if this works. This thing works. Alright. Now let's pull up the example here. So I think this is from Professor Dave. It's a rather simplistic view of image spaces, yes, but I think in order to like really understand an abstract concept like this. Oh wait! This has nothing to do with vector subspaces and everything to do with linear transformations. Right? I think it's linear transformations. Oh wait, no, this does have vector subspace. So we define a vector subspace as that. And we have a linear transformation within the vector subspace. So this is the example I was given. So let's say R3 is projected onto R2. So 3D to 2D. So basically, I don't know, like a normal like projector or something. It's pretty simple. And I guess our linear transformation would be the matrix, or not the, what is the, the linear vector transformation would be the following. Sorry, I wrote this weirdly. Be the following vector, the v1, v2 minus v3. If I wrote this slightly differently, then it's not a big. Okay, no, I got it correctly. So this is a pretty simple transformation, but I like it. It's simple, and it makes my job and my life a lot easier because I don't have to like overthink and do this. Actually, now that I think about it, I might be in my best interest. You know, it's fine. It's not a big deal. So we know vector space for the vectors to be the following. In 3D, so vectors in 3D are just v1, wait, was that right? V of 2, v of 3. So yeah, this is an average 3D vector. Alright? So pretty standard, typical 3D vector. And it's for any vector in V3. And then, so let's say hypothetically, we have our subspace, and our subspace is the following, right? Subspace emissary from Super Smash Bros. Amazing, by the way. Holy crap, that's like the only good part about that game. Anyway, so we have our subspace. It's 3C and then 0. It's just to make our lives easier. And then, now what do we do with the following vector subspace? Well, I want to plug this into this, right? So pretty simple stuff. So you just literally plug and chug basically. So our V1 is C, V2 is 2C minus C, 2C minus 0, which is just the following vector, C, 2C, and boom, our 3D vector gets transformed into a 2D vector. Let's say hypothetically, this is now 1. What happens? Minus 1, and then this becomes C minus 1. Let's say we have an actual this. What do we get? Well, 2C minus C is just C. Right? Okay, so this is just hypotheticals. I'm screwing around a little bit. Let's go back to the original name. But yeah, it's very simple, very straightforward linear transform. It's a hard concept, but again, in order to understand a hard concept, you want to start with the basics a little bit. So it's that. So now we go to the kernel of L, which is where things get complicated. So you have what is the kernel of L? That's what we want to. That's not the right name. This is the right notation right here. It's a kernel for kernel. So it's the set. So kernel, the set of vectors in subspace V, which gets Oh, no, 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 no. That give the 0 vectors in W. So W is just another vector subspace that we're projecting onto. 0 vector. Right. So, say for example, you have this V subspace. This is in R3. And then you got that basically projected onto R2 with W. Notations are weird. Yeah, so that's somewhat ish what I'm kind of getting at. Gives the 0 vector. So the 0 vector in V. So yeah, the 0 vector in V is projected as 0 vector in W. Right. So therefore, in order to solve for the kernel, we want to guess what? What do we want to do? Set our vectors equal to 0. Ding, 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 ding. So we have this and set it equal to the 0 vector. And what do we get? Well, V of 1 equals 0, and V of 2 equals V of 3. That is a bit weird. So, once we get that, we just kind of multiply, or not multiply, kind of like plug these vectors back into this essentially. And what do we get? We get 0, and then S is arbitrary. S can mean anything. S is arbitrary. I don't know if I spelled that word right, but S is arbitrary, could equal anything within the vector subspace. So, okay. So this is a set of vectors in L. And therefore, okay, now we prove that the kernel of L is a subspace of V, but we also know that the kernel of L is an image space. So the image space is what we're in W. So the image space is essentially just what we're projecting onto, right? Just think of projectors, right? Just watching, like, I don't know, it's a movie the kids are picking up, like Project Hail Mary, whatever. I haven't seen it. You watch that in the projector. Just imagine that. So you have a 3D projector emitting onto a 3D wall, what is essentially a 2D surface. Or actually, wait, that doesn't mean 3D projecting onto a 2D flat surface. That's kind of how you visualize it, right? Yeah. Okay, now let's do another example. Example 2. And then we're gonna get a little bit farther. Okay. Because we're gonna mainly focus on this. I'm gonna later, especially towards the end of this, focus on diagonalization and row echelon stuff. But that's not as important as this. We also need to focus on isomorphisms as well, but It's an isomorphism if it's the same dimension as the subspace, and it's non-isomorphism if it's not. So this time we're going from. Are we going from 2D to 3D? I think. Is that the example? 2D to 3D? Yeah. 2D to 3D. And our linear transformation of the vector is the following. And it's v of, what does it say? V of 2, negative 3, v of 1. It's a bit out of order here. And then actually no. V, 2v, is it 2v? 2v1 plus 2v2. We only have two vectors here because we're starting in 2D going to 3D. So this is a 3D vector projected from 2D. It's interesting. It's abstract. I'm sorry, this is all abstract. So if S is the subspace of vectors, S is the following 2D vector, or the following subspace, which is C of 0, so pretty simple. Find image L of S. So I'm going to find the projection essentially. So what do? This is simple. Plug and shove. You guessed it. Good job. So the second vector is 0. Third vector is just C. And then, yeah, that's about it. Right. Okay. Now we need to find the image, which I kind of I need to set it equal to 0, right? Is that the next step? Oh wait, no, that's the kernel. Wait, that's the kernel. So this is the kernel. So kernel of L equals this. Kernel's pretty easy to find actually. It's easier to find in my opinion. So oh wait, no, it's not. Wait. No. What am I doing? No. Find the kernel. Actually, wait, how do I find the image first? Am I stupid? Do I need to find the image? I think I need to find the image first. Oh wait, no, I need to find the kernel first. Okay, wait. So kernel first, set these equal to 0. 0, 0, 0. And guess what? Hold on. Get the set following 0 equals 0. 3C equals 0. 2C equals 0. Meaning these all 0, 0, 0. Yep. All the 0 vector. I think I might be doing something wrong. Please call me out if I am. I'm not even looking at this example here. If you know how to solve one, you know how to solve all, right? Is that how that works? Okay, wait, no, I was right. That was the kernel. Wait. If it all equals 0, then it's just the kernel. So then, wait. Okay, so this is the kernel of L. I'm so glad the air conditioning is working here. The air conditioning in the library, like a couple days ago when I don't know what I was studying for, but like It was so hot that I like almost fell asleep. It felt like I was gonna die of like carbon monoxide poisoning or something. So yeah, these all equal 0, then it just stays the same, I guess. I don't know. So now I need to find the image of us. Or the image of L, actually. How do I do that? I do not know. Basis of image. Wait, so that just becomes my basis factors. So then, so then the image would just be. I mean, it's the vector's being transformed, right? Oh wait, no. That is my image. And then my kernel would just be my kernel. Wait, so my kernel has to be in 2D. My image has to be in 3D. Wait, okay. Right? And then C equals 0, 0 equals 0. So that becomes the following 0, 0, and yeah. Right. Apparently that's the correct answer. I do not know. Okay. I guess I somewhat know how to do it. Let's do something a bit more challenging and brain nourishing, because that was kind of brain rot. Right? It's all brain rot. This is all brain rot, guys. And some people promised to join, they didn't. Okay. The next exam is going to be more complicated, meaning I probably preferably don't want to do it on this part of the whiteboard. Let's go to the other side of the whiteboard. Not that one. Oh. So yeah, a lot of these are definitions, by the way. So if I can get the definitions down, then I can get a good part of the test done, actually. So I just need to hone in on definitions, and then work on examples and with more abstract topics I'm less comfortable with. So that's kind of the study plan, which I'm focusing on the hardest, or not hardest, but like most the topic I'm least familiar with, which is kernels, image spaces, and isomorphisms. Maybe fall asleep, bro. Okay. It might take me a bit to pull up this next example, but let's see here. I'm gonna fall asleep, bro. This fan is like. I've been up since like 5 a.m. by the way. I get tired really easily, especially at 8 o'clock. I know. I get tired and then I like don't fall asleep. It's a vicious cycle. The my keyboard's not working. Okay. Good morning. 3, 3, 3. Let's get it. Math is fun. It's 3, 3, 3, 3. So yeah, kernel, and image transformation. And then we're gonna go to isomorphisms right after. Isomorphism is even more abstract. Actually, you know what would be good? Let me hop on Gradescope and look at the midterm, because I did not get that point. I'll just say that I did not get the point. Okay. So now that we kind of understand a little bit of the basics of isomorphisms, let's do a more complicated example that will probably show up on the final, which is is it 2 or 3? Or maybe it's more. Okay, yeah, here's the linear transformation. So I need to show that T is a linear transformation. Would it not be the same? So closed under addition. Okay, it's closed under addition. Scalar multiple, right? Okay. So I need to show the following right here. So we're gonna use black this time because black doesn't crack. Anyways, here's the following, kind of more common. You have the following linear transformation here. So we have a polynomial in 3D, or polynomials in the 3rd degree, and we're gonna transform that into R2, right? Right. And then we have the following transformation. So then T of P of X, Tp of X, transforms into the following P that is not a P. What the frick is that? P of 0, comma, P of 2. Yeah. For all P, what does it say? For all P of X as an element of the 3rd degree polynomial set. So this is a polynomial to the 3rd power. Just any in existence. So I could write it out as I could write it as a lot of things actually. Wait, first of all, I need to state my conditions. Okay, I'm gonna assume that it's the following, just kind of like a guess. So linear transformation is a linear transformation if it's closed under addition and if there is a scalar of real numbers. Okay, Okay, yeah, that's not doing too. Okay. So linear transformation if the scalar multiple two. What's two? Sorry. When's a scalar multiple? Closed under dish. Right. So those are the two ideas generally. I feel like I need to look at example polynomials if I want to actually do this. I'm going to look at a different example. I'm not going to look at the exact sample and copy off that. Basis of this stuff. Because this feels a little bit more abstract. Okay. So the polynomial set P3 set has the following basis of vectors. So it has 1x, x squared, x cubed. So it has this. So that is not, I don't know what that is. That is not, that's like a zeta or something. Or just, I don't know. I don't have to take this class back, but I hate myself. That's back to that. So you have the polynomial set P of 30. So then you get, well, the following. So then if it's a T of P of X, the transformation into R2 gives you the following, where the basis vectors 0, 0, 0, 0. Gosh, I need to prove this is a linear transformation first, do I? Well, how do I go about that? I think I have an idea. So, that's not an eraser. So, I got ahead of myself here, that's why. So, we can ignore that for now. We can actually copy this. I can read it, it's pretty easy. So, scalar multiple. So, let C be a scalar in the number set, and let's do T C P of X. CP of 0, CP2, right? I'm gonna check my answers after to make sure I'm not being stupid. And now you can factor this out. So then it becomes TC of P of X. Right. derivation for this part is this expression. So you have a scalar multiple for which. Did I prove it? Did I prove it? Actually, no. Okay. Which equals C T of P of X. C T P of X. So you can factor that out with scalar multiple for which, yep. And now the more complicated thing you have to prove closed under so let S of X equal P of X plus Q of X. Right. Wait, are transformations in the are in the subset of that? Okay, I need to find a closed addition in there before I get something very wrong. I feel like I'm doing something wrong there. It's funny because the other linear sections don't have to do this. This is really just linear involved. I'm gonna put that very so harshly. Okay. Well, okay, so what do we get? We get the following. We get P of Q of 0, and then P plus Q of 2. Which becomes the following. This comes back. We okay, so this just evaluates 0. This evaluates 2. 8. Select minus. Select minus 2. I don't think this is correct. Hold up, give me 1 second. Give me 1 second. This is, I don't think this is how you prove something. I might be really stupid. And prove linear transformation. And of course, the examples are so much easier. Okay, yeah. Okay, yeah. So I want to prove that. Okay. Whenever I did here, this is wrong. Right? Um, that is not how you do it. You know how to do one, you know how to do one. So this is the transformation of P3. P X plus Q X T. So then this transformation, since it's a polynomial of the third degree, you get the following. You get this is constant 3x 2 plus c x 2 plus x squared plus d plus cubed of 2. So now we evaluate the following. We get a, this all cancels out because we're 0, comma, a plus 2b plus 4c plus 8 d. Right. And now, how do I finish this? I have to figure this out. Okay, I need to combine like term. Maybe I just add this. I just add this. So I just add these two. So I just add to the following polynomial, which gives me the following a to b plus 4c b plus 8d. Theoretically, I could factor out 2. I don't know how relevant that is to this equation. records. I get this. Oh wait, no. Oh, okay. No. So then I add these two, and then it gets me. Let's see. Okay. I need to check my work because I can't tell if I'm like really wrong or not. I think I'm lost. I'm not gonna lie. I'm lost. Um. So I can turn that. We can theoretically turn this into a matrix with 2, 2, 4, 8. Sure. I can turn this into the matrix, the following matrix: 2, 2, 4, 8. A, B, C, D. Right. I can turn it into that. No, it's just, I don't know. Frick. Okay, I need to figure this out actually. This is not good. This is really not good. Okay. I didn't expect to get stuck on this, but here we are. Alright. Oh, it says the polynomial is at most of the third degree. Does that mean theoretically I could compute a not single, but like, I don't think that helps much. Why is this so unintuitive? Oh my gosh. Okay, I might be really stupid. I overthought this a ton. Oh my gosh. Okay. It's not as complicated as I thought. So, whatever I was writing here, get rid of that. That's stupid. And what we have instead is the following. So, we can move this to the other side. So we P of 0. Okay, let's just try it out. So first of all, T P plus Q is the following, which is this. And then you get P of 0 plus Q of 0, P of 2 plus Q2, and then go further, you get P of 0, P of 2, and then Q of 0, P of 0 plus P of 2, Q of 0 plus Q of 2 plus Q of 2. And all 9 equals just P, excuse me, this just equals T of P plus T of Q. It's really that simple. Okay. Again, sometimes the actual answer is simpler than you think. So this, therefore, so you want to kind of get from this form to this form here. So you kind of want to ideally get from the form of T of A plus B over to T of A plus T of B. That's what you want to do. So once you have that form, therefore, you can say it's now closed under addition. And you are done. Vote John Kerry 2004. Anyways, now that we have that out of the way, we now need to find the following. Find a basis and dimension of the kernel curve T. So, let's see this up here. Not bad erased it too much, but that's okay. Oh my gosh. Oh my gosh. So, whatever I did here is wrong. It makes no sense. Aside somehow by... So... And we can rewrite it as this. So then our basis is the following set. 1, x, x squared, x cubed. Alright. And now we need to find a dimension of the kernel. Dimension of kernel. So, we need to know this formula, following formula here. Oh no, we need to find the basis. Compute basis and the dimension of the kernel. So we need a. Oh wait, no. We need a basis of the dimension. So we know the basis of P3. So, okay, wait, hold on. Basis of P3 is the following. There's a proof for that. I'm not going to do it because I don't know what it is. And now we need to find basis of curve of T and dimension of the kernel of T. And what did we do to find that? Well, we need to find, well, our basis vectors here. So, not vectors now for the basis of the kernel T must contain a list of this consists of polynomials, not vectors in R4. So, the transformation, we go from, hold on, I need to remind myself what I did before. Again, just a quick reminder. So yeah, basis of the kernel. Yeah, it's the set. Okay, kernel is the set of vectors in V, meaning kernel of T is just the following. Kernel of T is the following in V 1, 0. Excuse me. So the basis, so the kernel, the basis vector is just going to be 1, 0, 0, 0, and then 1, 2, 4, 8. It's this set right here. Right, so yeah, this is the way I have video with things. So as long as I know that definition, right, is that it? So, okay, so first of all, we already know something simple. The dimension of curve of T is 2. And how do we know this? Well, guess what? 2 vectors. Is it? So we know that already, actually. It's a pretty simple thing. But how do we find the basis? The answer is I do not know, really. Okay. Okay, wait. Okay, so this is actually pretty simple then. So we said, well, we already have p of 0. P of 0 just equals a. P of 2 equals a plus 2b plus 4c plus 8d. And then we set both of these equal to 0. So that becomes a equals 0, a plus 2b plus 4c plus 8d equals 0. So we know is 0, plug that back in. Just obliterates it. Then we have 2b plus 4c equals negative 8d. You can factor these out if you want. We get following. If you want, you don't have to. Yeah, it says no. You don't have to do that stuff. I just did it because I love the factor because it gives me a false sense of control. So in general, oh wait, we can divide both sides by 2. I'm stupid. So if we do that, we get b plus 2c equals negative 4d. Which we can rearrange that to become b equals 2c minus negative 2c minus 4d. And then, since after that we go back to this polynomial here, and just plug things in. Alright, so when we get rid of, so then we get the following, so that a stays, we have minus 4c plus 4d plus 4c plus 8d. So that becomes a minus 4 plus 4c plus 4d. Get this, I guess. Wait, is that right? Wait, no, this is wrong. First of all, that's the first problem. So, this is, and then second of all, this a gets obliterated when a equals 0. this gets obliterated. And then now we can parameterize ish. We kind of want it to be. And then, third of all, this goes away. So just B. This is -2C. And this is -4D. Cubed. Cubed. As far as you right for so this is cute. I also like this marker. I really like this one. This is like one of the best markers I've had. Markers dry up so easily, it makes me so sad. These markers are like so useful in college, and yet. Okay. Sorry, I did a some of the quick thing but we sub those in, and we get the we get is that correct? Okay. Now we substitute the following back from the plus bx plus cx squared plus dx cubed. And then we substitute this back into b, this. Now we get the following: dx cubed plus cx squared plus negative 2c minus 4d x. And then, yeah, you don't have that anymore. And then you want to distribute the x term, so then you get the following: dx cubed plus cx squared minus 2cx minus 4dx. Right. And then after, what you want to do, again, I kind of need the step by step because I know what I'm going to do. And then you group by coefficients, or by three coefficients. So now that you have coefficients kind of grouped by C and D, you get the following. So you have cx squared minus 2cx plus dx cubed minus 4dx. And then we can kind of go from there. We should not have that. He'd get mad at me if I calculate the dimension first, even though it's so obvious. That's okay. So then I'd get the following: c of x squared minus 2x plus d of x cubed minus 4x. So you factor these out, and then you get your basis vectors. These two things, once you have those factors, these are your basis. So your basis vectors are the following. X squared minus 2x and x cubed minus 4x. Yeah, that's your base. Right. I should write this in set notation actually. I'll write this. And then you can do a sanity check by setting equal to each other and see if they intersect. I'm not going to do that unless it explicitly tells me to on the test. So therefore, now we have basis vectors. We have our basis of curve T. So basis curve of T just equals this, right? So now that we have that, what is our dimension of curve T? Dimension of curve T. Well, notice how we have two basis vectors. Therefore, dim curve T is just 2. It's the amount of basis vectors we have. Right. Right. Let me fact check. Right. Okay. Hopefully he doesn't get mad at me for just saying that, because there's no formula that this is. No, that would be so much more annoying if it was that. Okay. Okay, so that's how you do this. You want to like take a pause, take a breather, figure this out. Now, how do we check if it's isomorphic? Isomorph. If it's an isomorphic. Well, check if it's an isomorphic if the function is bijective, since we were transforming technically from the polynomial, the third polynomial, to the R2 plane, and that dim of P3 is equal to 4. And then the dim and the kernel is only equal to 2. Not an isomorph. Not isomorphic. Now I'm gonna check my work because I hope that's the only condition if it's isomorphic. And I hope I am fine. Not non-isomorphism. It's not an isomorphism. Not an isomorph. So you have a set of real numbers, set of imaginary numbers, which I made up. Oh, I didn't make them up. Some guy did. Oh wait, no. Okay, wait, no. Isomorphic is if the domain and the codomain have the same dimension. So they're the codomain, by the way. So no, it's not that. So yeah, that's what we have in terms of kernel and stuff. Okay. Now let's move on to something bigger, better, stronger, and unfortunately a bit more challenging. Or I don't know if it's more challenging or not, because this technically is less abstract, but also more tedious, depending. Well, it's tedious if you're bad at algebra, like I am, which is crazy because I'm literally taking like algebra, like extremely hard, difficult like, calculus and abstract nuts and 10,000 dimensions and 45, 6, 7, 1, 2, 3. But you know, that's okay. It's okay. I hate myself too. I'm gonna fail this last one. Okay, problem 3. Okay. So you have the following matrix. This matrix right here. And for the sake of this, I'm also going to challenge myself and calculate the characteristic polynomial, even though the characteristic polynomial is given to you, which I still need to know how to solve for it, right? Just in case. It's an easier. This is a pretty easy matrix to take the determinant of too, by the way. So it shouldn't be too bad. Intuitively, you have the eigenvectors here. So first of all, you need to find what a diagonal matrix is, which is just simply this. I know, it looks like a percent sign. But you have zeros here, and then your eigenvalues lined up diagonally. We also know that the trace of a matrix, just so everyone knows, is the sum of the eigenvalues. By the way, these applications, just to be clear, these applications only work for I need to make sure you guys can see this actually. So yeah, these applications, by the way, only work for square matrices, because you can't take the determinant of, say, this. No, you can't do that. Because if you were to try to like do this, you have to multiply like this. And this doesn't exist, and then it just doesn't work. Okay, every single determinant is a square matrix, and you also another thing you can't do. You can't. So for example, this is an 8. You can't find. You can't find the inverse of this. You can't find the inverse of a square matrix because in order to find the A of the inverse, you have to set equal to the identity name. In order to find the inverse, you have to set A equal to identity. So, and in order to do that, you have to do, and in order to that identity as well, the square matrix. It's this. Or is this in part 2? It's this in 2 by 2. It's this in 3 by 3, and so on. Oh yeah, here's another thing about the identity matrix is that it's special in a way that all of its eigenvalues, aka all of its diagonals, are 1. So it's a very good type of matrix here, and if you want to solve this, you use Gaussian elimination, make the left side into the identity, make the right side, and the right side will become your I1 using Gaussian elim to reduce row echelon form. By the way, reduced row echelon form for a square matrix is simply the following. Okay, I screwed this up. Just don't mind me. It's the following: 0, 0, 0, 0, 0. Oh wait, my bad. It's just row echelon form, which means you just get the identity matrix. Yeah. Whoops. We're gonna do row echelon root, reduce row echelon form later. But you want your left side to become this, and your right side to become, and then your right, and then what's your left side becomes this, your right side's gonna become of. But this is just like general theorem, elementary stuff that I learned early in the semester, and I thankfully have memorized. But anyways, so first of all, I'm just gonna assume already we can take the determinant of this. By the way, another condition: matrix is non-invertible if and only if the determinant of A equals 0. If the determinant of A equals 0, then A of 1 also does not exist. Alright? So we got, so I kind of jumped around a little bit here in terms of like matrices and stuff. But it's good to memorize the theorems, especially for me, because active recall is one of the most effective study methods. So you like figure out, oh, what am I doing? You know? But yeah, it's pretty simple. So, how do we take a characteristic polynomial? The characteristic polynomial is defined as the following: CA of lambda, or lambda, equals the following of A minus I of lambda. And by the way, lambda is just your eigenvalue. So it's just this and this and this. So ideally you want your diagonal matrix to look something like this with your eigenvalues filled in. So how do we do it? So first of all, we need to subtract our matrix A. Before we can take determinant to subtract our matrix A by the matrix the identity with its eigenvalues replaced by lambda. So this becomes lambda, 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 0, 0, 0, 0, 0, 0. Just like that. And now what do we get? We get the following. I messed up again. It's the other way. I am so sorry. I am so sorry. It's the other. I need to stop doing that because because when I tried that last, it's a pain. It's a pain to solve and it's incorrect. Okay, it's not going to be that complicated. If something is overly complicated and doesn't or doesn't resolve to something nice, then it's probably wrong. That's just kind of math intuition. And if that's not the case, then your professor sucks and you need to leave a bad review on RMP. Just kidding. Anyways, we get the following. We get lambda minus 3, lambda minus 2, lambda minus 2. Now 0 minus 0 is 0, 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 0 minus 1 is negative 1, and 0 minus 1 is negative 1. And now, we can take the determinant of this. So the determinant, we can cofactor expand along this, so we get the following. So we're going to first, so I think it's best in this case, we can either, since we have zeros on both, we can either expand on the cofactors of this first column or the top row. Which one do you guys want to do? Want to expand them? If you do you want to expand the first column or top row? Either way, it's going to give the exact same results. So it does not matter. Okay, so what do we get? We get the following. By the way, we don't even have to solve for the other two because these two just cancel out the zero. So we literally just get the following. So we get this times this just becomes 1 Right. Let me fact check here because it does provide me. Probably. Down. Oh wait. So that, and then you just set the ceiling to 0. So this becomes the following. Okay, so maybe I new determinants. Is this not? So before it was okay. What the answer provides is this, by the way, just so you know, it provides this as the answer. It doesn't provide this as the answer. Oh, by the way, clarification: we're solve for the eigenvalues characteristic polynomial always must equal 0 no matter what. But you know, since it's provided the eigenvalues anyways, I'm gonna just stop it right there. So we have our eigenvalues of the following. So, and you can also tell the eigenvalues and then base. Actually, no, you can't. I'm stupid. Yeah, just ignore what I just said. So the eigenvalues are the following: x for eigen of. What does it say? Does it want us to use the greater or lesser? Okay. By the way, despite having first of all, characteristic polynomial equals the following. What was that? So, what do we have? We have our first eigenvalue is equal to 1, and our second eigenvalue is equal to 3. Now, why don't we have a third eigenvalue? Well, that's because we cannot have two eigenvalues that equal to each other in this case. So if we have the same eigenvalue, so if we have two of the same eigenvalue, they just become the exact same eigenvalue. These two, having two of the same solution is consequential later, but for right now, just assume that. And we also know that eigenvalue 1 is greater than eigenvalue 2 because it just wants us to have. It just wants us to be like that. So. And now, next up, we need to find a set of basic eigenvectors. Set of basic eigenvectors. So this is our part A. Now let's go to part B. This is part A. This is part B. So now we need to find a set of basic eigenvectors for which associated with the eigenvalue of 1. So we have the basic eigenvectors of lambda of 1 following. It becomes 3a minus I, right? Right. Just to confirm. No. It's a minus 3i. A minus 3i. Or it's a minus this of I. Or it's, excuse me. It's the null space. So our basic eigenvalues are from the null space of a minus 3i. What is the null space? Well, I'll tell you in a second once I figure this out first. So our null space essentially okay, let me just refresh. Null space should be when the vectors are equal to 0, right? Yeah, so it's when the equation a times x equals 0. So yeah, you can find. Okay, yeah, okay, I figured it out now. Okay, so first of all, we need to find the null of the matrix. So we have a minus 3i, so then a minus 3, 3, 3, 0, 0, 0, 0, 0, 0. I'm not actually going to sign test because I don't want these points. But this becomes 0, 0, 0. Um, 0. Actually, hold on. The diagonals remain the same, so this is going to be 1. Or the non-diagonals, excuse me. So this is going to be 1. This is going to be 1. This is going to be 0. And when we care about our diagonals, so that becomes minus 1. And also minus 1. So that's our null space of it. Now the question is, we need to put this into reduced row echelon form, right? Is this in reduced row echelon form? No, not really. So we need to find the. Actually, first of all, we don't even have a. We don't even have a 1 value here. Okay, wait, hold up. Yeah, we don't have a 1 value in any of the first column actually. That might be a problem. Hold up. Okay. Wait. I was gonna say maybe I could just flip the rows, but I can't do that, and you can't do column when it comes to row operations, you can't change the columns. That just is not allowed. So, and you can't take a transpose either. Speaking of which, I didn't talk about transpose in so freaking long. Anyways, so let me. Do use matrix if the first column is 0. Oh, I just skipped it. Okay. Okay, wait, no. So then our null space is. So we're in the set of the A to the X vector to the 0. That's our null space. So, well, I need some therapy because I'm so iffy with null spaces, bro. That's like the worst last splits. It's when our vector equals 0, right? Wait, so hold on. So our solutions become X. So this top one, we have. Okay, wait. So then X is a free variable of T, and then Y, negative Y equals C, and then y equals negative z. So speaking of which, we have to figure out linear independence and dependence. Oh my gosh! Good thing I have another like 15 hours. That's so much time. Dude, this might be worth me the money. I hope I didn't go on the other thing. I'm so worried about that. Is it good? So no, if I add that top row, I get 0. If I add that bottom row. Okay, so if I add this to this 0, add to that 0, I just cancel everything out and make even more 3 vectors, which. Okay. T is arbitrary, by the way. T is arbitrary since we know x is a free vector. You know what? I might have to just cut my losses and see how it's solved. I'm not gonna do the full way, but I need to see like how to do this part because I'm a little bit lost here. And this is important for diagonalization, which I'm pretty sure. Actually, no, I'm not pretty sure. It's guaranteed going to be on the final. There is no way it's not. If it's not, then that's I don't know, bro. Gotta be. I know. Okay, what do I know? There's going to be an isomorphism kernel in image space. There's going to be diagonalization. There's going to be a reduced Gaussian question or Gaussian elimination question. Those are like the certainties. The other stuff I'm not sure as much. Oh yeah, there's a linear defect. Okay. Okay, yeah. So we do S. And we can set Y. Okay, wait, hold on. I did something wrong. I did something so wrong. Hold up. I did something wrong. So hold on. Hold on. First of all, let's let S okay, I did something so wrong. So S equals X equals S. S T R and then there are also numbers. So I would end myself if I had to work with anything else. And then negative y plus z equals 0. And then y minus z equals 0. So y equals z, which equals t. So that's our t. And then now we get our three eigenvectors as S of t, which equals S of 1 of 0, 0 plus plus t of 1, 1, 0, and then these. There's three eigenvectors. Okay, no, that's good. Okay. So then these are the eigenvectors. Eigenvectors I'd say there's 3 eigenvectors. Oh, wait. So then, hold on. So then, okay, the set of basic vectors is the following set: 1, 0, 0, 0, 1, 1. This is amazing. I love this. No one joined. No one joined my stream, I don't think. Unless someone did that, but that's really so cool. Hold on. No. Okay. So now that we have our set of basic eigenvectors, which is just these two, now we can move on to part C, or part 3, which is, so, now that we have our basic eigenvectors of the following, I'm going to erase this first, because I still need my eigenvectors. So we have our eigenvectors of x and y, and then we're given a third eigenvector of z. So, part C. So, we can turn that into the following matrix here. 1, 0, 0, 1, 1, 0. And then what is our z vector? It is apparently 0, 1, minus 1, if I remember correctly. Yes. So that's 0, 1, minus 1. And that's our matrix. What does it want us to call our matrix? Oh yeah, this is our P matrix. P matrix. Now, is it diagonalizable? Well, first of all, we need to check if it's invertible. Well then, actually no, first of all, we need to know the diagonal matrix is equal to the P matrix times A times the inverse of the P matrix. So, if we want to check if it's diagonalizable, we need to figure out, is P invertible? Is P invertible? So, what do we want to do? We want to take the determinant of P. Okay, this part I feel comfortable with. So we have 1, 1, 1, minus 1, 1, 0, 0, 0, 0. We expand along this. We get the following. 1, determinant, 1, 1, minus 1, 1. And we get the following. 1 plus 1 and 2, 1. So that gives us 2, meaning the matrix is invertible. Therefore, therefore, the matrix P is diagonalizable. Okay, so now that we know that our matrix P, now that we know that there exists a matrix D for which our matrix P is diagonalizable, we can do this the hard way where we find the inverse of this and then multiply it out and then, but too time consuming and you are bound to make mistakes. So how do we fix that? Well, we have our eigenvectors following. So we know that the diagonal matrix is just going to be the following. So we have lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0. So now what we need to do is just put in our eigenvalues. It's that simple. So you have 3, 1, 1. And we have 2 1s because our characteristic polynomial from earlier had 2 solutions for that. So yeah, our solution is the diagonal matrix of a 3 by 3 diagonal matrix, which is this, and that is our diagonal matrix D. And we are done. Let me just check my work, make sure I didn't screw anything up. Okay, so I feel like the problem before is not the step of like finding the diagonal, it's more so finding the basis vectors, because I feel like the basic vectors is a lot less intuitive than this part. Let me just make sure I did something right. Wait, it's 3, 3, 1. Why is it 3, 3, 1? Wait. Oh, wait, yeah, it's because, okay, wait. It's because our characteristic polynomial had 2 solutions for 3, and I thought it was 2 solutions for 1. Okay, just pretend I got that right. Okay. Moving on. Next subject, hopefully, becomes a little bit more intuitive as I go along here. Oh my gosh. So there's a lot of matrix computations here. Okay. Should I do linear independence first or should I do Gaussian elimination? I think I should do linear independence because I'm worse with that. Gaussian elimination, I can at least get some semblance of an answer even if it's off. Linear independence, I freaking don't remember that at all, so let's pull up an example. You know, I'm feeling risky. I'm going to use the Form B exam, which I did not take. Unless, actually, isn't the Form B just the same thing but different? You know what? It doesn't matter. Error while processing or retrieving the document. Okay, thank you, Canvas. I love Canvas. I love you, Canvas. I love you, Canvas, so much. Okay. Okay. I love Canvas. Oh my gosh. Dude, I pinged you guys. I pinged you 2 hours ago. They said they would, yeah, I'd be willing. And they were on voice call. And oh my gosh. Bro was playing Stardew Valley. Oh my gosh. Lucky person, done with finals. I love you. Okay, hold up. What is... Okay, well, I downloaded it. So, okay, first of all, I need to check, I need a definition for linear independence, okay? Definition of linear independence. So how do we define linear independence? Definition of linear independence. I feel like... So, there's multiple. Okay, so definition... So, here's the definition. Definition, I figured for this, by the way. Definition of... Oh my god. My hint... Okay, you know what? I hate this chair. I'm gonna move back. I kind of wanted to, like, kick it or something. I don't want to get in trouble and destroy the life that's probably. But that chair has been annoying. Also, this is kind of my callings. Okay. Definition. Definition. I don't know if I spelled definition correctly. Of linear independence. So we have it's conditions technically, whatever. One. Okay, I know the form, right? It's this technically. I don't know how to put that into words. Let me put that into words, because I'm autistic. I don't know how to use words. I only know how to use math. I'm actually bad at math. Okay. Okay. When none of the vectors in the set, my handwriting, can be written as a combination of another. Meaning, this is not actually. Right, okay. Meaning, wait, so this is that it? Okay, no, it's this. So it's v of 1 equals v of 2 equals v of 3 equals ... equals v of n equals 0. So all of the vectors equals 0. The scalars, however, do not have to equal 0. So they're dependent. They're independent from each other, and that's linear independence. Yeah, that's linear independence. Oh my handwriting is so atrocious. No, give me the key. Where's the okay. Hello, for me. So yeah. Okay, so I just determined. Now I have to determine the following. Is this suppose x, y, and z are linearly independent. Yeah, linear independent. Okay, so if that's linearly independent, then determine if x, y, the following set, x, y minus x of z is linear independent. I feel like I could raw dog this, and then just like say. So then this is our v1, this is our v2, this is our v3. So let's kind of do the following here. X equals 0, y minus x equals 0, z equals 0. But what do we have here? Well, this becomes y equals x. So are we linearly dependent then? But then x equals 0 means which means that y also has to equal 0, right? Okay. I need help. I mean, maybe I'm dumb. I feel like this is just a conceptual gap that I can bridge pretty quickly. Oh wait. No, I'm doing this wrong. Okay, hold up. I saw part of the answer key. I didn't see the whole thing, but I realized something. You need your scalars. Are the scalars equal or not equal? No, the scalars can equal 0. I know that, but okay, no, they're different. So hold on. So let me just redo this theorem here. So this is actually a v of 1 plus v of 2, or no, equals, right? Wait, is that, am I, okay, hold on. I just need to, no. Okay. C of v of 3. So, hold on. I was lied to. I don't know what website I got, but whatever that was completely wrong. So then, let's say K and then V of N. And in K are natural numbers. Or no, K is an integer and is a natural number in this case. It's arbitrary, doesn't matter. I took my discrete math final today. I'm a bit brain rotted from that. I don't know what I did. I think I got like an 80. There was the one about the binary set. We went over like those counting sets, like or the cardinality of infinite sets in like last second. It's not fun. But anyways, so we have a of x plus b of y minus x. The vectors there plus z c equals 0. Okay. So simple. Is it 0 or is it 0 vector? I don't know. It's conceptual. Who cares? We know it matters. But. So now we kind of have our a of x vector plus b of y vector minus b x vector. Wait, hold up. I'm going like step by, okay, yeah, this is correct. Wait! I just realized it. Okay, well, it doesn't matter. This is the same, essentially. I realize I'm doing a problem different from the one in the book, but it's essentially the same thing. So, we have what we have essentially, if we turn this into a minus b of x vector plus b of y vector plus z of c of z vector, and that equals 0. I love zeros. No, I don't. And now, what this becomes is frick. What this becomes is okay, wait, hold on. Okay, no. Wait, do I? Okay, wait. Okay, wait. So yeah. So this becomes the following system. A minus B equals 0, B equals 0, C equals 0. That becomes A equals B. Linearly independent? No, because we know B equals 0, so we plug that in. And that becomes A equals 0. So that means A equals B equals C equals 0. And that's linearly independent. Now, is that how they did that in the book? Because if it's not how I did that in the book, then I'll get like 10 billion points docked off. They didn't set it up as a system, did they? Oh, wait. Oh wait, also I kind of forgot to do this. What you're supposed to do is step before this, where like you have X. You're supposed to also show that this is linearly independent too, because someone told me that the scalars are supposed to be non-zero and the vectors are supposed to be 0. That makes no sense. I don't know why someone told me that. I really kind of got to myself. And since we already have our system solved, which is I don't know if he'd be fine with me writing it as a system. It's more intuitive for me that way. I don't know if that's how we did in the class. I mean, I should know. But yeah, so it's linearly independent if the scalars are 0. Okay. Now, so we're kind of just going through every topic here. How much time have I been streaming? 2 hours and 13 minutes, or almost 14 minutes. Okay. So this is what I have so far. Kind of like a general. What else do I need? Okay, we're gonna do Gaussian elimination now because this is the most tedious, but also the most rewarding. And I feel like some of these are gonna evaluate nicely. I did this example earlier, so I think I'm just gonna redo it because I like that example. So I'm gonna do the test. I think this one was on the test. This wasn't in the midterm. Actually, no, maybe it was a midterm. I don't know. This one, again. This is midterm 3. So, actually, there are solutions like how to solve this, how to solve that, but this guy has a full like GitHub page. I wonder what other courses he teaches. I kind of want to like look at his other courses actually now. Well, after I'm done with the final, and I end with like a freaking 65 because I'm stupid. But so yeah, we're not gonna look at solutions for this. I might want to do another. Okay, wait, hold on. B basis. Okay, wait, hold on. We need more conceptual things first and foremost. So we're gonna delay Gaussian elimination for a little bit because I feel like this is a good example. So V is the vector space of no, it's just V is a set. V is a vector space. And then B is a set of the following. B is a set of these vectors. Vector 1, vector 2, dot, vector. Was it conversion? It's inconsequential. A set of vectors in B. So, what does it mean? So, what does it mean for B to be a basis in V? So this is kind of like a basis. Is this the same or different from the subspace? I don't know. Okay. 3 conditions. Contains a 0 vector for which x of n is 0 vector. The closed addition. I'm gonna put a question mark because I actually not really so sure. And then there exists a scalar for which number set, or exists a scalar c for which scalar multiple now let's check my answers. I'm gonna be so wrong about this because I don't know anything. Explaining the basis. That's different. A basis is different. You have a basis. A basis would be like a basis would be like the vectors of the kernel. Not the kernel. No, it doesn't say kernel. These are the vectors within. Right? Okay, hold on. Okay. I'm so screwed. I am so screwed. Oh my gosh. This is what happens when you have a final on Friday at 3 p.m. 1. Oh, wait. Okay. No, this is wrong. Okay, this is very wrong. So there's only 2 conditions, actually. There's only 2 conditions, and none of them are correct. And none of what I wrote on the board is correct. So everything I wrote is completely wrong. Because I was thinking of this is a subspace, and it's not talking about subspace, it's talking about basis. So, number 1. The vectors within the set B are linearly independent. And 2, I don't remember what 2 is. Oh yeah, B is the spanning set. I need to say this one. Spanning set for V. So that would mean for every vector in V is a linear of this x1, x2, something like that. So yeah, those are the 2 conditions. It looks like 2 C's I wrote. And then yeah, I just probably X and A and this. That's not an idea. I'm gonna write this. A1 x1 plus A2 x2 dot 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 a of n of x of n that equals 0. Okay. I have to memorize this. Because I forgot this. And best way to memorize something is to practice, right? Right? Sure. Okay. Again, it's definitions. I did look at flashcards online earlier. Best way to do it is to, my final is thankfully later in the day, because today my final is at 8 a.m. I don't know if it's ideal. Like, it's best to review. I know it's best to review beforehand because you get better memory, that long-term memory that way. It makes it easier to retain the information if you learn something a couple hours before that, which is why I'm doing this now. Column space and oh gosh. Okay. Okay, yeah. Okay. So yeah, I just find subspace a little bit questionably because I kind of treat it more like a transformation. But let's consider this problem. So this is number 2 on the practice. So I like this problem a lot because it actually works out very naturally. So, by the way, we are doing gaussian elimination now because this is like the basics of the course. So we have A of matrix 1, 2, 3, 4, 5, 6, 7, 8, and negative 6, negative 8. Negative 10. Okay, negative 10, negative 10, negative 12. Now, Gaussian elimination is something that's like, say, for example, trying to solve for a system of equations. Well, if I were to try to do this out, like right now, I get like 1 plus 2 x plus 3 x 3 plus 4 x 4 and that equals 0, and then I have like 5x of 1. I mean, you can't. It's not like a typical like system of equations that you'd see like this, where you can just like simply eliminate stuff and then move on with your life. It's not like that, okay? It's something a lot more inconvenient. But how do we make something that would be as complicated as this into something as simple as this? Well, you have what is Gaussian elimination. So there are 2 forms of Gaussian elimination that I just need to clarify. One of them is not used as much later in the course as the other because one of them is just objectively easier to work with. So you have 2 forms of Gaussian elimination. You have this one, which is row echelon form. So row echelon form, the reason why I got its name is because it's based on a staircase. So we have a 3 by 4 matrix. So what do we do with a 3 by 4 matrix? So we kind of want, well, we kind of have the entries here. So 1 acts as kind of the entries. So the entries, like the entrance to each member. Each column with 1, by the way, and then the pivot column. And what's going to be below in the column of 1? It should be 0. It should be all 0. Right? And then we have this. So row echelon form, by the way, has the bottom row being all 0s for bottom row. And then what do we put in the 3rd and 4th row? I actually don't know. Hold on. Wait. Okay, I need to review. This just to be sure. I don't use row echelon form that much since I'm a bit rusty with it. Row echelon for definition. Just need to make sure it's Yeah, it's easier to work with a square matrix because, for example, if it's like if we have a 3x3 matrix, row echelon form would literally just be this. It's literally just this, right? 3x3. That would need for a 3x4. Wait, wouldn't it just be? Okay, let me clarify. Maybe I'm wrong. Maybe I'm right. Okay, so every pivot's one. Oh gosh, I'm bad at this. I might actually screw. I'm not gonna lie. Also, this is this is not a 3x4. This is a 4x3. Whoops. Okay. But again, I should ideally know how to do this with every form. Okay, wait, yeah. So the pivot is actually every other number. So it'd be this. Right. No, no, okay, yeah. So this is the row echelon form. So it acts kind of as a staircase-ish. What would the rank of this be? Rank of A is just equal to the number of pivots. You kind of think of it staircase, right? So then rank of A should equal 2, right? I actually don't know. I need to clarify. Oh no! Oh no, this is a pivot too. It's just not. Because the pivot is the one that changes also. Wait, this is a 4x4. Am I high? Am I a high? What? Okay, a 4x4 in row echelon form would be this. And the rank would be 4. Because there are 4 people. I think I may be. Okay, you know what? Let's just. Okay, I wasted my time. We're dragging this. We're dragging this too much. Okay, and now what is more important is 3x4 and reduce row echelon form. By the way, the term row reducing the term row reduced in the term echelon is just like staircase in French. It's 10:44. I'm gonna wrap this up. Okay, after this I'm gonna do one more example. Okay. So what is the form? Well, it's all zeros here. And then all zeros here. And then 1. This is an actual not a rhetorical question, I don't know. It should be this. And there's zeros above the pivot, right? Is that? Hold on. Okay, maybe this is wrong. Yeah, this isn't right. Okay, I need a better way to visualize these type of matrices. Okay. I was gonna say, if you don't know how to do this, you're cooked. That might be really cooked. But again, ideally you want it to be like, so you have like one variable here getting solved, and then less variables here. Actually, if I were to solve this, that would not be really because you do have two variables with one relation in this format. I know that, and I don't know how to put in reduce fraction format. Frick. What is it? Okay, so no. What I've been doing is wrong. So the pivot's here. 0, any number. 0 has to be above the pivot, right? And then this range of A would equal to, because there are two pivots. Right? Right. 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 Also, this is a solution. Wait, hold up. Okay, so after this, so there would be pivots every other row, right? For this, for that, for that thing. Yeah, I swear there's not a pattern to this, and I think that. That's okay. Okay. So and now I just know I need to get into this format. Okay, I think that's all that matters, really. As long as I know how to put this to this, I think I'm good. So, I want to do it for them. I need to write this up here so I don't forget myself. 1 dot 0 dot, and then this is 1 0 0 0 0 0 0. That looks too much like a 0. Okay, I need to get into this format. Alright. So, now, I'm getting so tired actually. Now, good news for us is that you're nice enough to already make this one. So now we need to okay, yeah. Okay. R3. We first of all want to make this. So we kind of like think about this like going from left to right, column by column, trying to make these into zeros and this into 1, right? That's kind of like our general idea here. So we want to have R3 minus simplicities R6 R1. That's our first row operation. So kind of the general types of row operations, I guess, if you want to write them down. Types of row operations. Probably don't need to know this for the test, but explain this for the test. But anyways, first one, you multiply slash divide the row. Okay, see these are pretty easy to remember. So like for example, you have this or this, so stuff like that. Next one, you add slash subtract rows. Yeah, like this. Or this. Yeah, it's pretty simple. And then you flip rows. So for example, row 1 can become row 2. I mean, can switch with row 2. So the transformation of this would be like A, B, C, D, E, F, G, H. This is not Euler's, by the way. Just ignore that. This is random variable, okay? E, F, G, H, A, B, C, D. Yeah, that's a simple. That's the simplest way to do it. Okay. I don't know why I define that. Everyone knows how to do that. If you don't know how to do that, then that's an even bigger problem than not knowing what reduced fractional form, right? Right. Okay, this becomes 0. 8 minus 12 minus 4. Negative 10 minus 18. Oh wait, no, it's plus. My bad. See, okay. See, I knew what to do. I just like forgot basic arithmetic, and then you can see the pattern here. 5, 6, 7, 8. Yeah, it's gonna be 9. So we already have a golden opportunity here. You see it, you know it. You can simplify this a little bit theoretically, but it's better to just take me straight. Take me straight there. So what do we want to do? Actually, never mind. It's better if we do this first. And then you can do this, by the way. This is valid. You can do 2 row operations at once. Just be careful what you're doing. Like, don't do something like this. Like, don't try to work on like 2 different rows at the same time that like contradict each other. It's too confusing. Just make sure you know what you're doing when you do something like this. But whatever the case. Wait, no. I'm getting ahead of myself actually. See? I'm gonna need to make sure. Because I realized that if I were to do this, then, you know, that would not be good. So, 1, 2, 3. 5, 6, 7, 8. 1, 2, 3. And now, our next step, now that we have our 0, let's simplify a little bit. We can, actually, I should have just done that first. You know what? Yeah, see, I should have just done that. See, this would have been fast. Oh my gosh. I'm a little bit sluggish and more tired. I've been awake since like 5 minutes, so give me a break here. So we have r of 2 minus 5 r of 1. And we get 0, 0. Okay, yeah. See, okay, now I remember why this worked out so well. And then okay, yeah, this is why it worked out so well. Oh wait, that's not. Now, neuron activation may tell you to just subtract or add. You can theoretically subtract. So which row do we want to get rid of? Now that we have a golden opportunity to get a 0 row here. Do you want to get rid of the second row or the third row? It's the second row. I mean, it's the third row. It's the third row. You want to get the third row subtracted, so it's all zeros, right? So this 0, 0, 0, 0. Don't even bother thinking about it. You're correct. Actually, these calculations are shouldn't be hard. And now that we have that, we want to make this entry here 0. So we do that by the following. 2 plus 2r1, we get Oh wait, no. I should have done something first, actually. Oh no, I got rid of that. Because the problem is that you have this. This zero right here is a big nuisance. Okay, I want to, for the sake of time, I'm just gonna like see what he did step by step. Again, I should know how to do this, but I'm stupid and I don't. So I'm so tired, bro. Okay. So he added. Oh, he added R3 to R1, and then he. Okay. Okay. Wait. Wait. This can be done in literally 4 steps. Okay. Hold on. So I'm doing this the unintuitive, stupid way. So my first step was right with that, and my second step was also correct. But I feel like I kind of got lost in the prospects of okay, so 5R2, right? Is that what I did? No, R2. Okay, R2 minus 5R1. So that should yield. So you're subtracting that 2 minus 1, 0, 0. Or do third row first. Eight. Right. For a 12, then -4, -8, -12. And then 1, 2, 3, 4, 5, 6, 7, 5, 6, 7. Are you rushing or redragging? I don't know. Dude, it's so hot in this room that I might actually fall asleep. Like, hot, I don't know about you, but like hot conditions make me so drowsy. Okay, and now I want to turn this into the first column. I'm technically doing it a different way from what he did, but I'm getting the same result. So, again, 0, 1, 2, 3, 1, 2, 3, 4, 0, 0, 0, 0. Okay, maybe I did this wrong. Whatever. No, I didn't. I'm fine. I'm up there. 4, and then I don't want to do row operations. Or adding up subtracting operations on the same row. Right. Wait. Okay, wait. Reduced row echelon form can either be that, or it can also be this. Oh, no. It cannot be that. It can also be this. Or this is 0. Right? Yes, okay. Good. So it can be either that, or it can either be that. As long as the... I like to think of maybe the rain can reduce row echelon form is just like the amount, the number of rows minus 1. So say 4 by 3 matrix. Number versus 4 minus 1. That's rank of 3. Right? This is this is not really mathematical. It's just some bullcrap I made up at the last second. Okay, yeah, now we want that 2 to equal 0. So now we subtract our 1 minus 2r2. That gives you 1, 0, 3, minus 1, 4, minus 2, 0, 1, 2, 3, 0, 0, 0, 0. So technically, we have the first, now we have all the rows in reduced fraction, right? Yes, yes, yes. Okay, now that we have that, it's going to ask for the following. I don't know why I just gained a British accent there. Okay. By the way, it's 11:01, meaning we have like 15 minutes, so this might be the last problem I do. It's a good problem though, because apparently I don't know anything. So it's the stretching. It's some area stretching factor. That was so cringe. I say this and I'm gonna fail this class. Kill me. It's been going on for almost 3 hours, and I've not done anything. Does Professor Leonard teach linear algebra? No, probably not. Man. Okay, now that I have this. So now that we have. Okay, wait, yeah, okay. So, that's number 2. Compute. And use it to give the row bases. So, our bases for row A. Row A. It's pretty simple. It's literally just the, what's it called? It's just the rows that aren't all zeros. So this is the row space of A. So you kind of want to use it as a set-ish. Yeah, set theory is pretty useful in linear algebra. That's why it's good to maybe take it with discrete math. Not that they're like hand in hand or anything, but like with the sets, it really does help. And then now the column space. So the column space of A yet to be more difficult. Because the column space of A, you might want to be telling me it's like, oh, there's going to be 4 different column spaces of A. No. The column space of A is actually your pivot columns in non-reduced row echelon form. So the column space of A is actually, believe it or not, going to be 1, 5, minus 6, comma, 2, 6, minus 8. I know. I was surprised by this too, but I just found out. But that's your column space. All right? It's weird, it's interesting, but you just got to be mindful of that, okay? You just need to, like, know what you're doing with that. So just remember it. I'm sure there's a proof for it. I'm sure I don't want to see that proof. But yeah. And use it to give. So yeah, those are your bases for rows A and B. I wonder if you want me to do it a different way. Okay, yeah, we did the same way, except we just wrote bases for length and like wrote an explanation on why. And now use it to set compute a system of basic solutions. Okay, yeah. So I just use. Okay. So my shoe fell off. So now that we have our row reduced matrix here, in Gaussian elimination, using Gaussian elimination, we can use that. Let's just get rid of this. Here, this is. Oh wait, no! I need that. I need that. I can erase most of everything else. Well, actually, I'm gonna keep most of this just in case. We can now use our reduced row echelon form matrix to do the following. So this is where it's going to comments down. So now that we have this, we can convert this into a linear system where we want to solve for the values of x equal to 0. So then x of 1, that's not 1, x of 2, x of 3 plus x of 4. And see, this is much more simpler to solve for, right? Well, actually, you can go for it. Well, no, you can't. Okay. I was visualizing how much can you reduce it? And you're like, no, reduced row echelon form is the most reduced you can go. So, it's unfortunate here. We'll have to set our free vectors. So, and we set our free vectors using which ones were our pivot columns, right? So we can set let x1 equal s, x2 equal t for some arbitrary s and t, right? Something like that. Oh wait, no, it's actually the non-pivot columns. So I got it completely wrong. Anyways, let's pretend that did not happen. Anyways, now we can go and solve for our solutions-ish. So we know the solution to x4 and the solution to x3 already. And by that we mean we technically just made it up. And now we kind of plug back in. So what is x2? It's a really good roller coaster at Six Flags Magic Mountain. But it's also the following solution, just negative s minus t. Right? Yeah, okay, so x2 is this. And now, x1, we can just solve the same way. x1 equals 2t plus s. So that's our basic solutions. Oh, I'm low-key high. I forgot about a bunch of stuff. So, let's run it back a second. 1, 2, 3. 2, 3. And I got the other ones right. So, okay, now let me actually solve. Again, it's stupid mistakes like this that you can't, that can really screw you up. So just, no, this is no calculated closed book exam, by the way, which is why I'm so screwed, but, I did get this one like that, but just thanks to that was wrong. Okay. Right. Five. Also, I'm losing my mind. I'm losing my mind with basic arithmetic. I'm losing. That's not supposed to happen. Wait, how is it? Oh, wait, no, it's S. Yeah, okay. Okay. S looks like 5 to me because my eyesight sucks. Which is funny because I write it the exact same way. Now, using part A, and then C, using part A, write compute a set of basic solutions to the system. Oh my gosh, this is so long. I'm getting so tired. So I'm assuming it's gonna be this, which is going to equal the following. It's gonna be this. It's gonna be this. And meaning set of basic solutions is the following set here, which is just 1 minus 2, 0. Again, when I know how to do something, I'm pretty confident that I do it. Except for basic arithmetic for some reason. But I'm gonna do well with it. Yeah, I don't even. I mean, I guess I should. Doesn't hurt. I'm gonna say I don't even need to check my solutions, but no, I should not be confident of that. There is. Okay, yep, that's correct. Now, using the vector of z. Now, okay, so now that we have our basic solution, this is back to diagonalization, essentially. So it kind of ties back in. This is different from diagonalization, but it's kind of similar. So now that we have our vector of z, or z, if you're not stupid, we can kind of form our own matrix here. The general solution. Write your answer as the sum of a solution to the system put together by the associated homogeneous system. So we can build our matrix here, our new matrix. So our new matrix, we can do this poor marker. I love this marker, but what's gonna die soon? I'm feeling sad about it. And then what's our z value, our z vector? Okay, when you see a z vector, that means it wants you to construct the matrix generally. I don't know how helpful this is to me actually. 1, 1, minus 1, 0. Yeah, that's our homogeneous. Okay, you gotta remember the definition of general solutions to homogeneous. Right here, answer the sum of the particular solutions of the general. The solute system together with the general solution. It's saying a lot of words that I don't understand, so I need to simplify this for myself. Oh, wait. So it literally just becomes, wait, no, I don't need to build this. I'm wrong. So this literally becomes following. I hate C as a variable, by the way. Yeah, it's used all the time. There we go. And that's it. That's really all I have to do. Right? Just need some clarification. Yep. So general solution. So the general solution So that's all I need to know for there. Maybe I should briefly look at an isomorph. I'd say mainly grind diagonalization. I'm good with determinants, believe it or not, actually. That's like the only thing I'm good at. So vector subspace I need to memorize. And then isomorphic just means different if it's same dimension or not. If it's same dimension, it's isomorphic. If it's different dimension, it's not isomorphic. It's pretty simple. I always love how these very hard STEM classes always have like the absolute like easiest end topic, except Calc 2. Calc 2 deserves to die. I hate Calc 2. But every other STEM class I've taken, so actually no, just kidding. Some STEM classes sometimes have a final topic that is easier than the rest of the STEM course. Sometimes, like Calc 1, Calc 3, and linear algebra. So it was actually oh no, there's different types of STEM. Sure. So yeah, it's mostly just definitions I need to remember, especially for this part and the multiple choice, true or false. It's just like definitions, definition of linearly independent, definition of reduced row echelon, definition of vector subspaces, and matrix transformations. I mean linear transformations and stuff like that. So just need to memorize flashcards. And I think that's going to be it for tonight. Thank you for showing up. I didn't read the chat wrong. I looked at the stream a few times. There was no one talking, so I just gave up. Thank you for tuning in, all 0 of you. Let's just one of you. That'd be cool. Yeah. This is for myself. Not that I think about it. An active recall type. But I think I have my work cut out for me now. And hopefully I can do well. At least, what do I need for an A in the class? I think 95. And then it is like 80 something, 81, 82. I don't know. It's worth so much in my grade that I hope nerfs it a little bit. Or, I don't know. That's something like an example straight off the book or straight off of the midterms. That would be nice. But anyways, just gonna do the slow, satisfying erasing. You guys want to hear? Is it enough for erasing ASMR? You guys still would get the. I don't have the spray thing, unfortunately. I feel bad because now it's going to be stable. Is there another eraser in here? There's a paper towel. It's pretty much out, so never mind. There's nothing. But yeah, that's kind of a general kind of thing. I know I didn't. There's a lot I didn't talk about. I didn't go in depth enough. Okay, what did I not talk about? Hold on. I need to double check because there's a lot of stuff I didn't talk about. Okay. Okay, I didn't talk about cofactor expansion or determinants. You know what? Actually, we have time. We have time to do one determinant. So this is going to be a pretty simple. We just do. I can make a determinant on the spot actually, just to make sure. Determinants, I feel like, are easy as long as you know what you're doing. So find the determinant of the 4x4 matrix. Also, so determinants need to be square matrices only. Meaning non-square matrices are yes, not invertible. So find the determinant of this. Now, when it comes to something, sometimes you can use Gaussian elimination to make determinants easier. But we really don't have a need to do that here. So what do we want to expand upon? Do we want to expand on? So you, in general, you want to expand on the row with the most zeros or the column with the most zeros. In this case, it's inconsequential. We can expand on either. So we can expand on the row here. And now, hold up, wait for it. 4 by 4 matrix, meaning we have 1 to the 4. Or, excuse me, negative 1 to the 4. Negative 1 to the 4. By the way, when doing these types of matrices, it like alternates. So like, for example, so like, if you remember, think back to Calc 3 of ij, km, the determinant of p, q, or d, what should I say this? T, T, p, d, r. Again, this is not a topic I need to know for later on. But think back to Calc 3, how you go about this. Well, you would take this times this, and then you would get following vector, or just I, but then you want a minus. Now, where does that minus come from? Well, it alternates when taking the determinants. So, for example, this is supposed to be negative, positive, negative, positive, just like so. Right, right. Actually, I don't know. I'm going to assume it becomes the following, and then I can check my work later. Actually, I'll do it after. So then, now that we're expanding along here, we ignore this row and this column. So now we just made a 3 by 3 matrix. Wait, no, that's of this. And now, what do we want to expand upon? Do we want to expand on this? Or do we want to expand on this? It's really doesn't matter because we're going to get 0 either way. So that's just going to become minus 3, 1 minus 2, 2 minus 3. And now take the determinant of that. So if I do this correctly, it's going to be minus 3, negative 4, plus 3. So that becomes negative 3. Which becomes 3. That's the determinant, I think. I think. I'm not 100% sure. Because, again, there's a lot of arithmetic errors you can make here. Maybe there's a conceptual error with this, and I'll read into it. But for the most part, it's just cofactor expansion. Expand upon it. Like, say if this was 1, then I'd also have to do another thing. Or if I wanted to expand upon this, let's do another thing where I might have to. Actually, no, I'm supposed to ignore this and this. That would actually be fun. No. Okay, wait. No. Okay. 3 and then times 1 minus 2, 0, plus 3, 0, and then minus 2. Oh, wait, no. So minus 2, 0, and all the value, all the value they have to split. It's just going to do it, meaning matrix is not invertible. And just by looking at it, it doesn't look invertible, so I'm just going to assume that's correct. Again, determinants, gotta be careful. But if you understand the cofactor expansion stuff, it will be fine. I can like read it over in like 2 seconds. Do like 1 for slip. Okay, got it. Because I did this early on the practice exam and I got it first time. So I don't know. I did determinants a lot in calculus. And it's been a minute since I've taken that class, but it's still fresh in my mind, at least the IJK stuff. Anyways, I think it's time to end the stream now. I've been dragging this on for a while. It's almost 30 minutes before midnight, and hopefully this all goes to long term, and then I get like a sleep buff, and then I get a 100 on the exam. Hopefully, please. Alright. Thank you for tuning in, all 0 of you. Appreciate you.